Okay. Today I want to finish up topic 6 really quickly, and then with the rest of the day I would like to give us an introduction to our next topic, which is principal component analysis. So I think today will be kind of fun. We'll look at a real data set, and I'll give you a preview and just a feel for what this principal component stuff is about. Topic 6, slide 48, begins discussion of what's called two-way ANOVA. In the univariate case, ANOVA, you can have one-way ANOVA, you can have two-way ANOVA. The one-way versus two-way, what that has to do with is the predictor variables. What predictor variables do you have? So let me draw a little bit here. If I have a response variable that's numeric, and suppose I have a categorical predictor variable, or we could also call it a covariate. It's a variable that we want to model with respect to. We might have a numeric response, like quantify your pain. How much pain do you have right now? And x1 could be control versus a pill that's designed to help against pain. If that was the case, then we might consider a model of the form y modeled in terms of x1. That tilde is just loosely, all I mean by that is we're going to model y in terms of x1. In R, when you do model statements, like with a regression model or ANOVA, R uses this tilde notation to indicate model something in terms of. So if I just had one categorical predictor variable, this would be an example of one-way ANOVA. Our y in this case is a univariate variable. I'm not talking about vectors and multivariate. Usual one-way ANOVA is when you want to compare the mean response between the levels of a single categorical variable. If we had an additional categorical variable, so I'll just say, well, categorical again. If we had an additional one, then we could consider a model in terms of both x1 and x2. So I'm going to measure your pain, the response, and model it in terms of treatment. Do you get the placebo pill or do you get the experimental pill? And I'm also going to control for your gender or your race. Now there's two predictor variables or covariates that are involved in our model. That's an example of two-way ANOVA. The one-way / two-way designation has to do with how many factors are we including in our model. One-way is one factor, two-way is two factors. So we saw in the notes a review of one-way ANOVA, and then showed how that translates to multivariate ANOVA. I'll show this slide. Here's the MANOVA table. There's an ANOVA table that is sums of squares. And remember, ANOVA is all about how much variation is there between the groups relative to how much variation is there within the groups. Same thing with MANOVA. The variation is now in terms of variances and covariances. So these are matrices now instead of scalar sums of squares. But it's the same idea conceptually. Two-way MANOVA is when you have a vector response, a numeric vector response, and you have two factors that you want to do inference on. We don't have to go through the jargon and notation of two-way ANOVA. Let me just show you this picture, these two pictures. When you have two-way ANOVA, you have two factors. You have like the treatment, did you get placebo or treatment? And you have, say, gender, or maybe dosage. Did you get low dosage or high dosage? Would be another way to do it. The key is there's two factors. Then you can talk about the relationship between factor 1 and the response. You can talk about the relationship between factor 2 and the response. And an additional consideration is whether those two factors interact with each other. Does the effect of factor 1 maybe depend on the level of factor 2? Whenever we have more than one variable in a model, we can consider the individual effects of the variables themselves, but we can also ask about and model their interactions. So here's a picture to illustrate what we mean by an interaction. On the vertical axis is the response. This is a hypothetical scenario. Some numeric response that we're modeling on the vertical axis. On the horizontal axis, we have information on our second factor. This is a two-way ANOVA problem. On the horizontal axis, we have a factor that takes 4 possible values, 1, 2, 3, or 4. Those numbers don't mean anything. They're just categories. So we could have called them A, B, C, and D just as easily. And then the colors, the different colored line segments, correspond to the first factor, factor 1. So in this picture, it's a two-way ANOVA problem, numeric response. There's a 3-level factor 1, takes 3 levels, and there's a 4-level factor 2. If we just looked at factor 1, you're comparing the green connected line segments to the blue to the red. So roughly speaking, the effect of level 3 of factor 1 is to raise the response on average. And the effect of level 1 of factor 1 is to decrease the average response. You can see red, blue, green, ordered in that way. Asking about what's the effect of factor 1 is like asking what happens green, blue to red while ignoring the horizontal axis. Just without respect to factor 2, what happens as you go from level 1 to 2 to 3 of factor 1? And similarly, if we wanted to speak to the effect of factor 2, we could look at the points for level equal to 1 versus the points at level 2 and level 3 and level 4. And without respect to factor 1, going from level 1 to level 2 of factor 2 results in an increase on average. Going from 2 to 3 results in a decrease on average. And from 3 to 4, a big increase on average. One thing to notice about this picture is that the line segments are parallel with each other. The green line segments are parallel with the blue, which are parallel with the red. An implication of that is that the effect of going from, say, level 3 to level 4 in factor 2, that effect of going there on the red curve or there on the blue curve or there on the green curve, the effect is the same regardless of the level of factor 1. Factor 2 has an overall effect that does not depend on factor 1. So this is a picture of no interaction between the two factors. The treatment effect is the same regardless of your gender, for example. Whereas the next slide is an illustration of an interaction. So now we have, it's the same scenario, two factors. The first one has 3 levels, the second one has 4. But the lines are not parallel now. The effect of going from level 2 to level 3 on factor 2, for example, depends heavily on factor 1. In level 3 of factor 1, there's a decrease on average. In level 2, there's a smaller decrease. And in level 1, there's an increase on average. So the effect of factor 2 depends on the level taken by factor 1. When you have multiple covariates or predictor variables, that's something that you always want to consider. Is there an interaction? The stuff that we're talking about is interactions. Do I need an interaction in my model or not? Is a common question. Grew up.
Are these not IIDs independent? They are not independent each other.
Say it again.
Are these not IIDs independently?
These are IID. So the question was, are these IID observations, right? We would say that this is an IID setup. So the data in this case would consist of triples. I would have for individual I the response and the factor 1 value and the factor 2 value. So I don't mean to say anything against or it's not a consideration of independence or not. It's all about the effect of the different variables. Let me show you something that will tie in with the last part of these slides. Let me change the notation here to be x's. And suppose that x1 is either 0 or 1. So these are just binary factors. Suppose it's 0 if you're given a control pill, and it's 1 if you're given an experimental treatment. And suppose that x2 is for dosage. So you either get a low dose or you get a high dose. I have two factors, two categorical predictor variables. Here is a model. I could say the ith response is equal to an intercept plus a coefficient for x1 and another coefficient for x2 plus random error. That's a model statement. looks a little bit different from what we wrote down as an ANOVA model statement. This is a regression model statement. So linear regression is where you have a response variable and you write it in terms of a linear combination of your predictor variables. This is one possible model. An alternative would be this one. An additional coefficient that equals the product, or that is for the product of x1 and x2. The first one does not allow for an interaction, whereas the second one does. Let me just say something briefly here. The interpretation of beta 1 is the mean change in y associated with changing from x1 equals 0 to x1 equal 1 while holding x2 constant. The interpretation of that coefficient beta 1 is the effect of variable x1. Because there's not an interaction in the model, it is with respect to x2 being held constant. So it's kind of like the average effect of variable 1, where we've averaged over the levels of x2. Whereas this coefficient is mean change in response associated with going from x1 equals 0 to x1 equal 1 when x2 equals 0. The point I'm trying to make is, depending on whether you have an interaction in your model, it impacts how you interpret the coefficients. The red beta 1 is like an average x1 effect averaging over x2. If you put an interaction in the model, then the green beta 1 becomes an x1 effect that's specific to one of the levels of x2. So by including an interaction, you allow for there to be a separate x1 effect. There's an x1 effect for x2 equals 0, and there's a different one for x2 equal 1. So question, what's the difference between green and red? And in the red, I said this is holding x2 constant. And in the green, I said when x2 is 0, which is also constant. The red is applicable. That interpretation applies regardless of whether you hold x2 constant at 0 or 1. So no matter what x2 is, beta 1 is the effect of x1, holding x2 at its level. In the green case, beta 1 is only the effect of x1 when x2 equals 0. And there's a different effect when x2 equals 1. So I know where your question, I see where your question came from. In both cases, we're holding x2 constant. The distinction is that the green beta 1 is specific to a specific value of x2. Putting an interaction in the model means that you have effects of one of your variables that are specific to values of the other variable. If x2 is 0 in this second model, then the interaction term goes away. That's right. Let me show you one more thing here. Let's consider this model again. Beta 0, beta 1, x1i, beta 2, x2i, beta 3, x1i times x2i. Another way to write this is that the expected value of yi equals that linear combination. I got rid of the epsilons because the epsilons represent random variation and they have mean 0. So an equivalent way of writing this is that on average, the average response equals this linear combination. So we can interpret things carefully. Watch what happens if we say if x1 is 0 and x2 is 0. That's a subpopulation. That's the control group in, say, males. If we code it males are 0, or no, I did low versus high. So x1i 0 means control. x2i equals 0 means low dosage. So control, low dose. If you plug in x1i equals 0 and x2i equals 0 in the model, this corresponds to saying the expected response is just equal to beta 0. For individuals in the control group who got low dosage, my model says that the mean is beta 0. And we can do this for all other possibilities. Suppose we say x1i equals 1 and x2i equals 0. So this is the treatment group, low dose. Here we're saying that the average is equal to beta 0 plus beta 1. So just looking at these two statements, the interpretation of beta 1 is the difference between these two means. The bottom one, beta 0 plus beta 1, is the mean in the treatment group low dose. In the middle, the top one is just beta 0. That's the mean in the control group low dose. So how would you interpret beta 1? In words, what is beta 1? It's the mean difference comparing treatment to control in the low dose group. Beta 1 is mean change in response comparing treatment to control in low dose group. Let's write out the other combinations. If x1i equals 0 and x2i equals 1, that's control group, high dose. According to our model, the mean for that category is beta 0 plus beta 2, period. Beta 0 plus beta 2. So the interpretation of beta 2 is the mean change in response comparing high dose to low dose in the control group. And then finally, if both of them are 1, that's treatment group high dose, we have that the mean is equal to beta 0 plus beta 1 plus beta 2 plus beta 3. Beta 0 plus beta 1, right there, is the mean in the treatment group, low dose. Beta 0 plus beta 1 plus beta 2 plus beta 3 is the mean in the treatment group, high dose. So let me come back up here. Beta 0 here is the mean response in control low dose group. Beta 1 is a mean change in response. It's comparing treatment to control in the low dose group. Beta 2 is a mean change in response, comparing high to low dose in the control group. And then we have this last expression where beta 3 Beta 3 is a little harder to write out, but what an interaction term is a difference of differences. What I mean by that is beta 3 is a comparison of the effect of factor 2 in the control group compared to the effect of factor 2 in the treatment group. Beta 3 is an interaction term. Interactions are all about allowing for the effects of one of the predictor variables to depend on the level of another one. So we actually interpret beta 3 as that quantity, the difference in the effects. Going back to the beginning of what I've been writing here, the way I have presented this problem, where we have treatment or control and we have high or low dose, this is an ANOVA setup because we have a numeric response and a couple of categorical predictors. The notes express ANOVA models in a particular way, and they present these tables, sums of squares or covariance matrices and stuff. The way I wrote it here, with a response written as a linear combination of predictors, this is regression, linear regression style model statement. In your topic 6 notes, at the very end is some discussion of regression. So classically, multivariate statistics, in your book as well, in your textbook, there's a chapter or two on MANOVA, and there's a chapter on what they call multivariate linear regression. One thing I want you to see is that ANOVA and linear regression are actually the same thing. This problem right here is an ANOVA problem, but I wrote it as a regression problem. You can always do that. ANOVA is just regression and vice versa. Uh-huh. So if you add an interaction to your model, suppose the p-value, or suppose the sign for beta 1 hat goes from positive to negative, right? And suppose it goes from significant to not significant? Not significant to significant. How do you deal with that, or how do you interpret that? The key is that with or without an interaction term corresponds to two different models, two different assumptions. The model without the interaction assumes that the treatment effect is the same regardless of dose, and the dose effect is the same regardless of treatment. If you put the interaction term in there, then the interpretation of your coefficients changes. Beta 1 now becomes treatment effect in the low dose group. So if you had say a positive coefficient of beta 1 without an interaction and a negative one with an interaction, that's not necessarily inconsistent with each other. They're two different quantities. Beta 1 in the first case is like an average treatment effect, whereas beta 1 in the second case is the treatment effect specific to the low dose group. Those could be different. Similarly, the statistical significance could be different. There could be no overall treatment effect when you average over dosage, but there may be a treatment effect in the low dose. So let me just write one thing here, and that is that ANOVA is the same as regression. And on the whiteboard, I've written basically an ANOVA problem as a regression model. Multivariate statistics, for historical reasons, is heavy on ANOVA and MANOVA. But if you understand regression, you understand ANOVA, is the claim. In the notes, topic 6, at the end, is multivariate linear regression. And so let me just make a couple of comments. In the context of regression, there's what's called simple linear regression. This is where you have a univariate response, and you write it as a linear function of a single numeric predictor variable. So in this model, y and x are both scalars. Y might be BMI, and x might be average number of daily calories consumed. There's also multiple linear regression. Some books might actually call this multivariate regression, but we're not going to call it that. We're just going to call it multiple linear regression. So it's a univariate response, and I have a predictor variable, but I have additional predictor variables. So I might have average number of calories consumed, but I also have height in centimeters and some other things. But it's still univariate regression because the response is univariate. And then we would have multivariate regression. And that's where y is a vector. Beta 0 is a vector. Beta 1 is a vector. So the distinction between multiple linear regression and multivariate linear regression is that the response is actually a vector. I don't have time to go into multivariate regression much in our class, but I want you to at least be aware that it's out there. And the theory, the interpretation of model coefficients is comparable to the univariate regression setting. Slide 85 underscores what I said a moment ago about ANOVA being linear regression. So if you get confused, like, well, what's the difference between ANOVA and regression? Comfort yourself with they're exactly the same. They're just they're the same problem written slightly differently. ANOVA is regression where the covariates are categorical, I should specify. Okay. So let's wrap up topic 6 there. You now have tools to do multivariate inference on a mean, or a difference in means, or 3 or more means. That's a big toolkit. You can do a lot with that. The next chunk of material will kind of be a change of subject for a little while. But we're going to see a few topics within the category of exploratory data analysis. The t-squared stuff in MANOVA is modeling, it's inference. It's like formal statistical analysis. We're going to compute p-values and confidence intervals. Before doing inference with any old data set, you should always look at the data first. Just basic pictures, basic exploration. There was a famous statistician named John Tukey who kind of paved the way, I guess, for that way of thinking. Step 1 with a data set is to look at it. If you don't look at the data, make pictures, look for unusual patterns or unexpected things, you could get deceived by a fancy analysis that you just click a button to do. Are there missing values in your data? Are there outliers in your data? Are there values for your variables that are not possible? Do the patterns and relationships in your data go in the direction that you expect? Those are the types of things you want to make pictures and compute basic summaries to get a feel for. So let's suppose we have a multivariate data set. It's an n by p matrix of numbers. and I want to look at it. I want to make pictures of this data set. There are definitely things we could do for one variable at a time that are not complicated. We have p variables. I could go to each variable and make a histogram or a box plot. That's a good place to start. Let's look at each variable individually. But with multivariate statistics, we're counting on there being interrelationships between the variables. And just making a histogram or a box plot doesn't tell me anything about interrelationships. So we could think about doing one at a time graphs like histograms, box plots. Going in the direction of looking at interrelationships, we could maybe make scatter plots. For all pairs. Let's take x1, make a scatter plot with x2. Now let's take x1, make a scatter plot with x3. You could make all the pairwise scatter plots. Look at each one of them, and it gives you just an informal view of what the interrelationship is between those two variables. But what in the world could we do to, in one picture, characterize all the interrelationships at once? So we're going to learn about two, maybe three techniques, well, several techniques for visualizing our multivariate data in a way that's slicker than one variable at a time. So let me give you, we're almost out of time, darn. Let me give you a brief intro. So techniques that we will consider for multivariate investigation. We will see what's called principal component analysis. Principal component. We will also see what's called cluster analysis. Those are the two that I'm going to emphasize, but within these there are other examples, like very similar to PCA is something called factor analysis. With categorical variables, there's something called correspondence analysis. With distance-based data, there's multidimensional scaling. But the big idea of principal components is to take an n by p matrix of numbers and kind of cram it down into a smaller dimensional representation. Suppose we have 15 variables. So I have some sample size by 15 columns. If I could translate that somehow into just 2 columns, then I could make a scatter plot of my data. My entire data set, I could look at it in one picture. PCA is a technique for essentially doing that. It's a dimension reduction technique. Let's take our p variables and redefine them in such a way that we can have a handful maybe, instead of our total P, maybe just a handful that collectively give us basically the same story as all of them, but doing it with much fewer variables. Dimension reduction. And then cluster analysis is a discovery technique where we're trying to discover groupings in the data. If I have n individuals, and for each individual I have these p variables, can we discover, here's a subset of our individuals that all tend to have similar values on the variables. And here's a different subset, and here's a different subset. So these are what I call bread and butter tools for statistics analysis. Anytime I have a data set, I make these pictures early. They're a great way to get a rough, big picture feel for your data set. They show you much richer pictures of your data than just one-at-a-time graphs. And they often reveal some rather deep relationships and structure in a data set. So next time, Monday, I'll spend some time doing a little bit of review, and if we have time, I'll dive into PCA. As soon as we can get into PCA, we'll go to R and look at a couple of data sets. I think the funnest part of PCA is seeing it in action. Here's a big data set. We do this magic trick called PCA, and look at what we just found. You can find some interesting stuff. All right, out of time. So I'll see you Monday.